Hello everyone, welcome to the second session of Bridge Course for BTech Engineering Chemistry. Myself, Dr. Chandrasekhar, and I will be taking through today's class. Okay, so recollecting whatever we saw in the earlier section, so we discussed about different types of water, right? Before that, we saw what are the impurities present in the water, right? And what are the standards has been used to determine our water as hard water and soft water. And later we saw the cleansing action of soap when it comes in contact with water, either it is hard water or soft water, right? So we saw all these things in our first class, right? In today's class we will be seeing the hardness of water, right, which we already discussed. We will see a small glimpse of it once again, and then we will see different types of hardness present in the water sample, and then we will see the units what have been used to determine the hardness, that we will see, and at the end we will see how to determine the hardness present in a given water sample using EDTA method. Right? So this is the content for our today's class. Okay. Before going into the next topic, we will see some of the things whatever we saw in the last class. Right? So to recollect, and then we can easily go to our subjects. Okay. Right. So there are two types of water, whatever I said in my earlier class. Right. So two types of water. One is hard water, and the other one is soft water. What do you mean by hard water? Hard water is nothing but if the dissolved components are in a range of greater than 180 milligrams per liter, then those waters are called as hard water. And what are soft water? Soft water is if the amount of dissolved salt is less than 180 milligrams per liter, then we call them as soft water. Okay, so this is the two types of water whatever we saw in the last class, right? And additional to this, so this hard water, when soap is added to it, it will not lather, right? This also we saw in the earlier class. Hard water, when it comes in contact with soap, it will not form lather, right? Whereas soft water, when it comes in contact with soap, it forms lather, right? The chemistry behind this lathering and not lathering we saw in the last class. Okay, so it's mainly the component of soap which gets self-organized, and it will form a complex, or it forms a precipitate, and it precipitates in the solution in hard water. Okay, so all these things we saw in the earlier class, so we are not going to say it once again, but the thing what we have to take here now is hardness. What is hardness? So that we have to see. Hardness, by definition, it is a measure of the amount of dissolved hardness causing salt present in the sample. So this is the definition for hardness. Hardness is, it's a measure of the amount of dissolved hardness causing salt present in the sample. What are these hardness causing salts? Mostly, this also we discussed in the last class, mostly the hardness causing salts are mainly due to calcium and magnesium. Right? Mostly the hardness causing salts are calcium and magnesium salts. Maximum. There will be other salts also, but the percentage of calcium and magnesium will be higher. So we literally take it as hardness causing salts are calcium and magnesium salts. Okay? So this is first. The second property of hardness is, it is the property of the water not to lather when it comes in contact with soap. So this is the property of hard water, right? This is not the definition, but you can also write this as a definition for hardness, right? So it is the property of water not making the water to lather when it comes in contact with soap. So this is the property of hard water. We can put it as, it is also the tendency of the contents of the water sample to stop lathering in presence of soap. Right? So this is what I have given. Right? And the third one, as I said, the hardness are mostly because of calcium and magnesium salts. So this is the definition for hardness. Now we will see what are the different types of hardness present in the sample. Okay? So different types of hardness. There are two types of hardness. Okay, depending on the amount of or the content of salt present in the water sample. right? So there are two types of two types of hardness. One is temporary hardness and the other one is permanent hardness. There are two types of hardness. One is temporary hardness and the other one is permanent hardness. Why it is called temporary hardness? Because the hardness whatever caused by those salts can be easily removed. That's why it is temporary. Right? It cannot stay for a longer time. It can be easily removed by some process. Okay, so that's why those salts are called as temporary hardness causing salts. Right? So these temporary hardness is nothing but salts which can give you a hardness which can be easily removed when you treat it with some chemicals or some by process. So this is called temporary hardness. The hardness which can be easily removed by a simple process is called as temporary hardness. What is permanent hardness? Permanent hardness cannot be removed completely, right, unless otherwise you use a very harsh conditions. Okay, permanent hardness is the hardness which cannot be removed easily by a simple process, but you need a very harsh conditions to remove the hardness. So types of hardness, two, one is temporary hardness and the other one permanent hardness, right? Temporary hardness, the hardness causing salts can be decomposed or can be removed by a simple process, right? And permanent hardness is hardness which cannot be removed by a simple process, but it requires very stringent condition and a very strict it requires a very expensive conditions. Okay, so this is permanent hardness, right? So let's see what are the salts which causes this temporary and permanent hardness, right? So temporary hardness causing salts are mostly carbonates and bicarbonate salts. Temporary hardness causing salts are mostly carbonates and bicarbonates. Okay, so most of the carbonates are insoluble in water. So those carbonates can be easily separated by mere filtration. Okay, so temporary hardness causing salts are mainly due to two salts. One is carbonate and the other one is bicarbonate. Carbonates are insoluble in water, so they can be easily removed by mere filtration. Whereas the dissolved bicarbonates in the sample, that can be removed by simple boiling. Okay, so the bicarbonate salts which has been dissolved in water can be removed by mere boiling. What happens when boiling? This heat converts this bicarbonate into a carbonate with release of carbon dioxide. You can see the equation there, right? Bicarbonate, when you heat it up, it forms a carbonate plus carbon dioxide and water molecule. This carbonate, as I said, carbonates are mostly insoluble in water, so they will precipitate in the sample. Once it gets precipitated, you can easily remove the salt. Thereby, you can easily remove the temporary hardness causing salt. Right? So, because of this reason, temporary hardness is also called as carbonate hardness. Because the component is mostly carbonates and bicarbonates, so temporary hardness is also called as carbonate hardness. That okay? Right? So this is how a temporary hardness can be easily removed by mere boiling and filtration. Okay, clear? Right. So what is permanent hardness? Hardness which are caused by salts apart from carbonates and bicarbonates are called permanent hardness, right? So some examples like calcium chloride, calcium sulfate, nitrate, phosphate and silicate, all these things are permanent hardness because they cannot be easily removed. That stays in the sample itself. You need a special technique or a harsh conditions to remove this permanent hardness causing salt. Okay, so permanent hardness is mainly due to salts which are apart from carbonates and bicarbonates. For example, chlorides, sulfates, nitrates, phosphates, silicates, those are all permanent hardness causing salts. And these permanent hardness causing salts cannot be removed easily by mere boiling or filtration, but you need a very harsh condition to remove it. Right? Okay. So, some of these temporary and permanent hardness, we call it as total hardness. Okay, so once again repeating, temporary hardness is also called as carbonate hardness because the salts which are responsible for temporary hardness are carbonates and bicarbonates. Clear? Right. And permanent hardness causing salts are other than carbonates and bicarbonates like chloride, sulfates, nitrates, phosphates, silicates, all these things. Okay. And permanent hardness is also called as non-carbonate hardness. Temporary hardness is carbonate hardness and permanent hardness is non-carbonate hardness. Sum of this permanent hardness and temporary hardness is called as total hardness. Right? The sum of temporary and permanent hardness gives you the total hardness of a sample. Right? So what we saw what is hardness. Hardness is nothing but the measure of the amount of hardness causing salt in a water sample is called hardness. And the property of hard water is to stop lathering. So this is hard water. Okay, and mostly the salts which are responsible for hardness are due to calcium and magnesium. Okay, the other salts are there but they will be in a lower level. So calcium and magnesium will be in the highest level. Then we saw the types of hardness, two types of hardness. One is temporary hardness, the other one is permanent hardness. Temporary hardness is also called as carbonate hardness and permanent hardness is also called as non-carbonate hardness. The name comes because of the components present in it. Temporary hardness is mainly caused due to carbonate causing salts like carbonates and bicarbonates. Okay, whereas permanent hardness is caused by salts apart from carbonates and bicarbonates. Sum of permanent and temporary hardness will give you the total hardness of the sample. Right? Okay, so if this is understood, we will go to the next thing. If this is clear, we will move on to the next topic, how to express the hardness of our water. So we saw it is the amount of dissolved salts. So this amount, how we are going to express? To express this amount of hardness, you need a specific unit, right? Okay. So there are different units practiced, but we can't express always in grams. When you do an analysis, you will get in terms of grams, right? You can't express in terms of grams. We have to compare it with a standard material and then you have to give the number, right? So this is how you have to express the hardness of water. To express the hardness of water, we specifically use a system called as calcium carbonate equivalence. To express the unit of hardness or to express the hardness, we use a special term called calcium carbonate equivalence. And this calcium carbonate equivalence can be calculated if the weight of hardness causing salt is known. Right? So hardness is expressed in calcium carbonate equivalence, and if you know the amount of hardness causing salt present in the sample, then you can easily calculate the calcium carbonate equivalence by using this equation, which goes like calcium carbonate equivalence will be equal to weight of the hardness causing salt, weight in grams of the hardness causing salts into equivalent weight of calcium carbonate divided by equivalent weight of hardness producing salt. Okay, this is a very simple equation which can be remembered and we can practice it with the different amount of salts. Right? So for example, if the hardness is caused by calcium sulfate, right? So you will get the amount of calcium sulfate present in the system. Right? So you will put the weight there and you multiply it with equivalent weight of calcium carbonate divided by the equivalent weight of calcium sulfate. Okay? So if you put that one, then you will get the amount in calcium carbonate equivalence. Okay? So this is how the hardness is expressed regularly. Okay? So now a question arises. Why we have to choose calcium carbonate as a standard? Right? What is the need to take calcium carbonate as a standard? Calcium carbonate is chosen for this because calcium carbonate is highly insoluble in water. Compared to any other salts, calcium carbonate is highly insoluble in water, so that this has been taken as a standard. This is one reason. And the second reason is this calcium carbonate is commercially available at a cheaper price. This is the second reason. And third reason is its molecular weight is 100 grams. Right? Its molecular weight is not 100 grams. Its molecular weight is 100 atomic unit. Right? So its molecular weight is 100. So if you have this number, the calculation becomes very easier. The molecular weight is 100 and equivalent weight is 50. So the calculation becomes easier. Because of these three reasons, calcium carbonate has been chosen as the standard to calculate calcium carbonate equivalents. Clear? So the question arises, why calcium carbonate has been chosen as a standard? The answer for this is, the first one is calcium carbonate is the insoluble salt, maximum insoluble salt present, and it is commercially available, and it has a molecular weight of 100 and an equivalent weight of 50, which makes the calculation easier. So these are the reasons why calcium carbonate has been chosen to calculate the hardness for calcium carbonate equivalents, in calcium carbonate equivalents. Okay, right. So moving on to the next one. It's a very simple one. So how to express? So now you have to express in terms of different units have been proposed. So the most commonly used one is parts per million, or milligrams per liter, or milliequivalents per liter. So these three are the most commonly used units to express hardness of a sample. Right? So parts per million is nothing but it is 1 part of calcium carbonate equivalent of hardness present in 10 to the power 6 parts of a water. Right? It is 1 million. Right? It's 1 million. So parts per million. 1 is to 10 to the power 6 parts. That is 1 by 10 to the power 6 parts. So 1 ppm will be equal to 1 part of calcium carbonate equivalent hardness present in 10 to the power 6 parts of water. This is parts per million. And what is the next one? The other unit, milligrams per liter. So this is the amount of sample in milligram dissolved in 1 liter of a sample. Right? Mostly this 1 ppm is equal to 1 milligrams per liter. So the calculation is given here. You can see it one by one. Right? So it is very easy. So we are not going into details because we don't have time. So but the total, the parts per million, 1 parts per million will be equal to 1 milligrams per liter. So this is how it has been calculated. There are other units, as I said. So hardness can be given in degree Francis. It can also be given in degree Clark. As I said, it is also given in milliequivalents per liter. So this table gives you an idea of the different units and how each unit has been related to each other. Okay, so you have to remember any one line, and if you remember that line, then it becomes easier for you to calculate, to estimate the hardness or represent the hardness in different units. Okay, so these are the different units used to express hardness. Right? Okay, so now coming to the last part of our class, which is nothing but estimation of hardness of water by EDTA method. Right? So this is the topic which we are going to see. Right? So why this method has been chosen? The method was chosen because the accuracy of the measurement, the accuracy of the results whatever you are going to get by this method is very accurate. The errors are very less, and this reaction or the process is very fast, and you can get the result very easily. And the other one is the reaction or the process is very simple. Right? These 3 points make this estimation very simple and more convenient to do it in a lab. Right? First one is the accuracy is top notch, it is good, and the procedure is very simple, right? And the results can be obtained at a very faster rate. You can get the results in 10 to 15 minutes, right? So this is why this method has been chosen for estimating the hardness of water. Okay, right. So now we will see what is the principle behind this hardness, behind this EDTA estimation. The principle for this EDTA method is complex formation. The principle behind EDTA method of hardness estimation is complex formation. Right? What is a complex Complexes are nothing but organic and inorganic molecules forming to form a coordinated, with a coordinated bond, forming some colored system. Right? So why this has been chosen? Because the hardness causing salts are mostly metals. Right? Those metal salts will have electron deficient sites in it. Right? So these electron deficient sites are looking for electron rich species. So if any electron rich species like an organic molecule or an organic ligand with lone pair of electron, it will form coordination bond very fast. So this coordination bond will be very strong, and this makes the complex very stable. Right? So this is the main principle of this complexometric titration. So complexes are formed between the electron deficient metal and then electron rich organic ligand. So it forms a complex, and that complex is very stable, and it also gives you some color. Right? That is the main thing. So most of the complexes, since it is formed by metals, right, these metals have d orbitals. Because of these d orbitals, there will be dd transitions happening. There will be excitation of electrons and lowering of electrons. So this transition gives you the color for complex. Right? So if color is formed, then it becomes very easy to see the change in the reaction. Right? So these complexes are mostly colored in nature, which makes them to be identified in the analysis very easily due to color change. So this is an advantage of this complexometric titration. Right? So this is the principle behind EDTA titration or EDTA method of hardness estimation. Okay? Right. So now we have the principle. Now we have to choose what type of molecule we can choose as a ligand, right? So the organic molecule which has been chosen is EDTA, right? What is EDTA? We are talking about EDTA. What is full form of EDTA? EDTA is ethylene diamine tetraacetic acid, right? The name is nicely given. Ethylene, CH2, double bond CH2, that is ethylene. So when it forms a bond with diamine, so two amine at both the ends, this double bond will break. One will go for NH2, the other part will go for NH2. So NH2, single bond, CH2, single bond, CH2, single bond, NH2. Right? There are two hydrogen atoms at both the ammonia molecules. These four hydrogen atoms can be replaced with acetic acid molecule. Right? Acetic acid is CH3COOH. Right? So when it makes a bond with this ammonia molecule, it will be NHNCH2 C double bond OH. Right? The structure is given in the board. Right? It is ethylene diamine tetraacetic acid. Right? So this is the molecule chosen. Right? But EDTA has got a problem. EDTA is not soluble in water. If it is not soluble in water, we can't use this EDTA for our analysis. So what we have to do is, we have to convert this EDTA as EDTA into its disodium salt. Right? So EDTA is insoluble in water. So you are going to convert this EDTA into a soluble product, which will be disodium salt of EDTA. Disodium salt of EDTA structures. Two hydrogens are replaced with sodium ions. So this is EDTA disodium salt, and this disodium salt is soluble in water. So now we can use this disodium salt for our analysis. Another additional advantage is this disodium salt is commercially available and it is very cheap. Right? So this is an added advantage for this EDTA. Okay? Right. So this EDTA, which has got 4 oxygen molecules, 4 oxygen atoms, which has got lone pair of electrons, and 2 nitrogen atoms, right, which has got 2 lone pair of electrons. Altogether 6 lone pair of electrons are there. This 6 lone pair of electrons can be used to form a complex when a metal comes in. Right? That's why this EDTA has been chosen. EDTA is ethylene diamine tetraacetic acid. This 4 acetic acid molecule will give you 4 lone pair of electrons from oxygen, and the 2 nitrogen atom has got 2 lone pair of electrons each, so there will be 2. So altogether 6 lone pair of electrons will be there. This 6 lone pair of electrons will be used to form a complex when a metal comes in contact with it. Right? And the structure of that complex is shown here, where the metal atom will be at the center and all the complexing groups are covered around this metal. Right? The metal can be calcium or magnesium. If it is apart from calcium and magnesium, you can represent it as M. M represents metal. So this is the complex whatever is formed in when EDTA comes in contact with a metal. Okay, right. So this is the complex. Now we have another issue with this one. The issue is, as I said, complexes are usually colored in nature. But the problem here is the complex of EDTA with metal salt is colorless. The problem here is the metal EDTA complex is colorless. Okay, where you take hard water, you add the disodium salt of EDTA, it forms a complex, but that complex is not colored, so you will not be able to visualize whether the complex is formed or not. So even though EDTA is a better chelating agent and better ligating molecule, the color is not formed, so then it becomes useless. To make this useful, what we are going to use is, you are going to add an indicator to the system. Okay, indicators are organic molecules, right, which gives change in color because of complexation. Okay, so the indicator whatever chosen for this EDTA method is eriochrome black tea. So the structure is given here, which has got one sulfonic acid group, 2 hydroxy group and 1 nitro group. Along with it, it has got an azo group at the center. Azo is nothing but N double bond N. Right, azo group is N double bond 1 N. So this azo group is the one which gives color to this system. Okay, so this is eriochrome black tea and this is used as an indicator for EDTA estimation, and the beauty of this EBT is it changes color when the pH changes, or depending on the complex also it changes its color. Two things, EBT changes its color depending on the pH, that is one, and depending on the amount of complexation the color also changes here, right. So you can see here we have 3 different colors at 3 different pHs, right. At a pH less than 6.3, which will be in the protonated form, both the OH groups are in the protonated form, at that time the color of this complex or this molecule will be red in color, right. So at that time the color of this complex of this molecule will be red. At pH 7 or in between pH 11 and pH 6, the color will be blue. Okay, because of partially protonated hydroxy group. So it will be blue in color. And if it is at higher pH, both the hydroxy groups will be deprotonated and that color will be yellowish orange in color. So this is what the color change when this EBT changes, when EBT is present in different pH. Okay, along with this, right, so this monoprotonated, deprotonated EBT, when it comes in contact with metal, it forms a complex and that complex will be wine red in color. Right, you can see the wine red complex there. So where the one EBT molecule reacts with a metal and it forms a complex, and that complex is wine red in color. So you can see these equations also here, where the metal salt, when it comes in contact with the indicator at a pH of in between 6.3 and 11.5. So the color of that solution will be blue, and once the metal comes in contact, it forms a complex, and that complex will be wine red in color. So that is the structure of wine red complex when metal forms a complex with EBT. Right, it is common for both calcium as well as magnesium. Okay, right. So we have this complex, and as I said, the anion of EDTA will have 6 ligating groups, right? And this 6 ligating groups, when it comes in contact with metal, it forms a complex. This we already saw. Right. So this wine red color complex is not that stable. right? So there will be stability for all complex. This wine red complex is not that stable. If any other ligand comes in contact which has got a more complexing tendency, then this EBT will be replaced by the stronger ligand. Right? So the complex whatever formed by metal and EBT is not very strong. Whenever a better ligand comes, this EBT ligand can be replaced with a better ligand. So when compared to EDTA, EBT is slightly lesser stable. So when EDTA comes in contact with this complex, EBT will be knocked off and EDTA will form the complex. Okay, so the stability of EBT metal complex, which is wine red in color, is not stable when compared to the complex formed by metal EDTA. So when this metal EBT comes in contact with EDTA, EDTA will knock off this EBT and it forms a complex with the metal. Right? So that is the equation given here, right? So Y represents the EDTA molecule and H2 represents the two acid hydrogens present in the system, and the wine red is already represented as magnesium and D represents the EBT. So what happens here? So the metal changes its place and it's now attached to the EDTA complex, and the complex form is given here for both the calcium and magnesium. So these are the principles in which this EDTA estimation is done. Right? What we are going to do, first we make a complex of metal EBT which is wine red in color. Then you add EDTA and this EBT will be replaced by this EDTA, right? And at one point when all the complexes have been converted into EDTA, this wine red color changes to colorless metal EDTA, but at the same time the free EBT which was removed, that will give its blue color. Right? So during this titration what happens? So the complex is formed by metal EBT, and if it comes in contact with EDTA, it replaces the EBT, and the color of that EDTA complex will be colorless, but the free EBT which has been liberated, that will be blue in color. Right? So then we will observe a color change of wine red to blue. So this color change, the point at which the color changes, you stop the addition of EDTA and estimate and take a note of the amount of EDTA used. From the amount of EDTA used, you can calculate how much amount of metal present in the system. So this is the principle of EDTA measurement. Okay, right? So we will go one by one with the procedure, right? And then it becomes easier for you, right? So the chemicals whatever required for this estimation is 0.01 molar of standard disodium EDTA salt. This is one. Second, you need eriochrome black tea, which is nothing but your indicator. And third, you need a buffer which is made of ammonium hydroxide and ammonium chloride, which maintains the pH at around 10. Right? This pH buffer is very much important, because if pH is not maintained, the color changes will not happen. As I said, the color change, the EBT will show color depending on the pH. If the pH is not changed, the color will not change. It will be either in the red form or it will be in the yellowish orange form. Right? So we have this buffer has to be added, and this buffer will give you a pH of 10. Right, so that the color of EBT will be at blue. Right, so this buffer, pH buffer is very much important here. And the next one, whatever you need for analysis is a sample hard water, right, and a sample of hard water. Right, so these are the things, and then we use our regular glassware like volumetric flask, our conical flask, burette, pipette, beaker, and weighing bottles to do the experiment. Okay, right. So the procedure goes like this. First, you pipette out 20 ml of sample hard water which has to be estimated. You pipette out 20 ml of sample hard water into a conical flask. to this conical flask, which is this sample water is having hardness causing salt. That is, it might have calcium carbonate, calcium chloride, magnesium sulfate, or all these salts are present in this water sample, right? So metal salts are present. To this, you are going to add few drops of EBT. So when you add this EBT to this water sample, there won't be any color change. Can you know why there won't be any color change? Because the pH of this sample is not at an alkaline pH. So if it is not in alkaline pH, the color will not be observed. So the addition of EBT has to be done in order. So once you take 20 ml of sample, you have to make this sample in an alkaline form or at a pH of 10. To make this at pH 10, you are adding 2 to 5 ml of the buffer solution, which is nothing but ammonium hydroxide and ammonium chloride mixture. 2 to 5 ml of buffer solution you are going to add. Once you add this, the pH of the solution becomes alkaline, and now if you add the EBT few drops, then the color changes to wine red. And what was this wine red color? This wine red color is due to complex of the metal ion present in the water sample with the EBT added. So the color is due to the complex formed between the metal and the EBT solution. Right. So now you got this wine red color. Right. Now you have to titrate this with a EDTA solution, which is filled in our burette. Right. So now we have to titrate with the EDTA solution. As I said, EDTA is a stronger ligand compared to EBT. So when EDTA is added, right, what happens? EDTA will replace the EBT. Right. So EBT will be free and EDTA will form a complex. Right. So you start adding EDTA in drops until what? Until the color changes from wine red to blue. Right. So that is the place where all the metal ions have formed a complex with EDTA, leaving behind EBT free. So you titrate continuously until the color changes from wine red to blue, and you stop the titration once the color changes. Note down that value. Right. So that will be the volume of EDTA used for color change, and you represent it with V1. V1 is volume and 1 represents for EDTA or VEDTA you can put. And the molarity of EDTA is nothing but 0.01 molar, which is already taken. Once you get this one, and you can equate it to the other solution, which is your sample, and that sample, we know how much volume we have taken for that sample, which is nothing but 20 ml. But we don't know the strength of it, right? So that molarity is zero, is unknown, right? So if you equate this with the famous equation, M1 into V1 is equal to M2 into V2, where M1 and V1 represents the molarity and volume of EDTA, and M2 and V2 represent the molarity and volume of unknown water sample. So in this one, in these 4 components, the unknown component is M2, which is the strength of the water sample. You cross multiply it, reshuffle it, and you will get an equation of M2 will be equal to M1 into V1 divided by M2. So with this substitution of all the data, you will get the M2 value, which has been tabulated in this slide. Right? For example, you take 20 ml, it has been taken, and you titrated, and the volume came around 16.5 ml, and you substitute all these things, and you will end up with a molarity of 0.00825 molar of water sample. Right? Using this equation, you calculated the molarity of this sample. Right? So, as I said at the start, hardness is usually represented in ppm or milligrams per liter or calcium carbonate. right? To convert this molarity into calcium carbonate equivalents or milli equivalents, or in ppm, you have to use this equation where you multiply this molarity with molecular weight of calcium carbonate and 1000. So this will give you 825 ppm. So this is the hardness of water. Right? So this is how we have to do this, and this has to be repeated to get a concordant value. If the values are not concordant, then you have to repeat until you get, right? Once you get this concordant value, and then you can calculate this, and this will give you the total hardness of a sample. Right? Any idea how to measure the temporary hardness? It's very easy, right? So those details we will see it in the class, how to make and all those things. But it's simple. I already told in the class, at the start of the class, how to remove temporary hardness. You simply heat the solution for some time, right? Where all the temporary hardness will be converted into calcium carbonate or magnesium carbonate. That will be precipitating. You filter that solution and you take that solution which is free of temporary hardness, you titrate it with the same procedure, right? You will get some molarity, or you will get some ppm of hardness. So that will give you the permanent hardness value. So that will give you the permanent hardness value if you use the water sample which is boiled and filtered. So you got total hardness, you got permanent hardness, right? So if you minus total hardness, if you minus permanent hardness from total hardness, whatever you get will be temporary hardness. So this is how all these three hardness can be estimated using this EDTA method, right? Total hardness is equal to permanent hardness plus temporary hardness. Permanent hardness can be measured by boiling the sample, right, and doing the estimation and titration, whereas total hardness you can get by using the raw water sample. So when you minus this, you will get permanent temporary hardness, right? So this is how hardness can be estimated. Okay, clear, right? So to summarize, we started with definition of hardness. We saw different types of hardness. What are the components of those hardness we saw. Then we saw the different units in which this hardness can be represented, and then we saw the method to measure the hardness of a sample, which is nothing but EDTA method. We saw why EDTA has been chosen. Then we saw what is the principle of this, what are the equations involved in it, what are the complexes formed we saw, and then we saw the procedure in which by which you can do this experiment, and then we saw the calculation how hardness can be estimated. Right? And at the end we saw how to calculate total hardness, temporary hardness and permanent hardness. Okay, so hope this bridge course has given you a small idea about how all these things can be done. Okay, so we will see all these things in detail in our regular classes. Okay, so which will be more interesting because we will be adding more inputs in these analysis and more informations in this analysis. That will be interesting. Okay, right. So we will stop here, and if you have any doubts, please contact me through my mail. So I will be available to respond all these questions, right? And there are some questions which has to be given. Please go through these questions, and this will give you a better idea about this processes and about the principles whatever used for these analysis. Please do answer all these questions, right? And if possible, we will discuss in the next class. Okay, thank you for your attention. Hope to see you in the next session. Okay, and thank you.